At Digital Science, it's no secret that we love data. But data itself is useless unless you can make sense of it. So to turn that information to impact, you need a way of ordering that data. Now, one such way is by using knowledge graphs. And today's Speaker Series guest is an expert on those and more. We're really excited to be joined by Dr. Danny Hillis, the founder of Applied Invention. Danny, thank you so much for joining us today. I'm going to start with the biggest question of all. Now, given your career, I have no idea how you're going to sum all of this up. But can you tell us a little bit about who you are and what you do and how you've got to doing what you do?
All right. I was extremely lucky that the first thing that I worked on was building the fastest computer in the world. I built one of the very first parallel computers. And so for many years, the little company I started built the only really parallel computers, so they were the fastest computers. Now the reason that was extremely lucky is it caused all kinds of interesting people to come to me. Mm-hmm. And so I got most of my education by people who sort of came to use my computer because they had some very complicated problem, and then I would have to understand the problem. Mm-hmm. And so I got to learn about astronomy and geology and airplane design and credit card marketing and a whole bunch of things that I never would have gotten any insight into from the people who were on the cutting edge of that. And after a while, I realized that actually solving these complicated problems was actually much more interesting than building computers. And so that's eventually led to the company that I've founded now, which is Applied Invention, which is, in some sense, the company of last resort that people come to if they can't solve a problem and they're not quite sure how to solve it. So it's a bunch of people who have interdisciplinary set of experience. Actually, some of them from back in the days of thinking machines, when we made these very fast computers, people come to us with complex problems in agriculture, or aerospace, or medicine that they see a business in, and they see that there's a need for something, but they can't quite make something that works that solves the problem. And so when somebody comes to us, we put 3 tests on it. One, our first test is anybody really excited about this around here? And actually most problems just fall off because nobody's that excited. If it's like, a new kind of spam filter or something, it's not that interesting. But generally we get excited about things because we think they could potentially have some big impact on the world. And then the second test we do is, can we make money on it? Or can we at least not lose money on it? And so that's evaluated by a different person than the person who's excited about it. And the third test that we do is we say, is there some reason that we believe that we can solve this problem better than other people can? And if there is, it's almost always because it's interdisciplinary. So we have mechanical engineers, we have biologists, we have chemists, we have programmers, we have optical designers. And it's actually very rare to have all those things together in one place. So generally when you go to someone to solve a problem, you're asking them to take their hammer and to pound down your nail. But we have a lot of different kinds of hammers, and so it's not. So generally we end up solving things in ways that are different than the people expected us to solve them.
I'm going to pick up on the interdisciplinary nature of that shortly, but I would love to just take a step back to thinking machines, because you mentioned very casually just some of the people that you worked with, some of the people that almost, were there at the very start. Can you tell us a little bit more about some of them and the impact that had, and the impact that thinking machines still has to this day on the world around us?
So the Thinking Machines was the first company to make really parallel computers with thousands or tens of thousands of processors in them. And it was made specifically to make artificial intelligence work, and what we'd now call large language models and things like that. It was very clear that those would need a lot of parallel computing power. And so Thinking Machines was an acknowledgement that the ordinary computers wouldn't do that. You'd need a different kind of computer. Now, at the time, it was thought that parallel computers didn't work in general. The chief architect of IBM, Gene Amdahl, created a declaration called Amdahl's Law, which basically proved that the more processors you put on a problem, the less efficient it got. And so it was generally believed that Amdahl's Law couldn't be broken. And so there was remarkably little attention put into making parallel computers. But since I was interested in artificial intelligence, I was working with Marvin Minsky. I knew that the brain is a parallel computer. It has very slow components, and yet we do things very quickly. So even if Amdahl's Law applied in general, I knew it didn't apply to artificial intelligence. So that was the goal, was to build a machine that could do artificial intelligence. Now, it turns out I was a few decades too early, and we didn't need 10,000 times as much power. We needed 10 million times as much power. But in the process of it, we ended up building these very fast machines, which did get used some for artificial intelligence research, but they weren't fast enough to do the things we do today. But they also got used to, for instance, make the first global climate models, or the first three-dimensional seismic models, or the first stealth aircraft, or a whole series of things they enabled. Actually, some of the first data mining of credit cards was done on them. And so it turns out that all the problems we looked at, they were actually useful for. So everything turned out to be an exception to Amdahl's Law. But the fun thing about it is because it attracted super smart people. So, for example, when I was first trying to found the company, I went around to my friends that were professors and asked them for students that might work at the company. And I went to Richard Feynman and told him what I was doing, and said, "Do you have any students I should hire, or at least have as summer interns?" And Richard Feynman said, "No, none of my students are crazy enough to do something as kooky as a parallel computer when it's known that's not going to work." He said, "But I do have somebody who doesn't know much about computers who's crazy enough to work for you, and he's pretty smart and hardworking. So maybe you could hire him, but for the summer." And so I was like, "Great, do you give him, if you recommend it?" And he says, "Oh, I recommend him 100%. And I was like, "Okay, what's his name?" And he said, "Richard Feynman." And so he was actually my first hire.
Brilliant.
But as soon as you get really good people like that involved, it becomes easy to get other people. And so we had people that were just gigs. We had, Sidney Brenner before he was a Nobel Prize winner, or come to use the machine. Or actually, Eric Lander, who was not in biology, got interested in the genome and realized he could use this machine to handle it. And he did some of his first biology projects in that. And so we ended up having, a tremendous number of extremely smart people just came because of this resource. And of course, they were all teaching each other what they were doing. And so that's how it got this sort of interdisciplinary start to it. And it turns out that almost all other situations reward specialists. But this was a way that you could kind of be a generalist. And the thing that brought it together was the sort of big computing. But in the end, we didn't even need that. Actually, a lot of the projects we do use a lot of computers, but some of them don't. Some of them are more mechanical, optical, things like that. So it was a fantastic company in terms of intellectual environment. It was way ahead of its time, which is not a good thing for a business. So it didn't work as a business, but it worked great as an environment. I still run into people who say, it was the best job they ever had.
Oh, wow. I mean, you had impacts, lasting impacts on science and society, but even popular culture. Did I read somewhere that one of my favorite authors, Neil Stephenson, actually used one of your computers?
Neil Stephenson, the science fiction writer, was we had many people who heard about the connection machine and somehow managed to get time on one. Wow. Neil Stephenson's original idea for Snow Crash was it was going to be a computer program. Right. And he realized he needed a much faster computer. So he got the manuals for connection machine and learned how to program it. And eventually decided it was too hard to program it. So he just wrote a book about it. And that was his first science fiction book. Goodness. And so that's kind of, it wasn't the first, it was his first published book, I guess. And so another person who had access to connection machine was Sergey Brin, who worked his search engine, his search engine ideas out. Yeah. And, in fact, a lot of how Google does things, the whole sort of way they use MapReduce was sort of how the connection machine worked. And so actually, it turns out that thinking machines it was too early. You could have made a lot of money if you had just invested money in all the people who used the computer. Because it turned out, people really went on to do fantastic things, but there were people who were stretching the possibilities, and that's why they were using this, because they were trying to do something that was just outside the possibility of what you could do with normal machines. So I guess I kind of got addicted to that stretching the possibilities kind of work. So somehow I managed to do that for a living. And then once you start doing it, and then it's sort of self-sustaining because, of course, there's no place to advertise for this kind of work. So all our customers come in by word of mouth and some other, somebody's seen us solve a different kind of problem.
Yeah. You mentioned Google. I wanted to talk about, we've had a lovely couple of days getting into the weeds about knowledge graphs, about, taking a huge amount of information that can be disordered and trying to gain insight and information from it through aligning it alongside some kind of order. So you were quite involved in the Google Knowledge Graph project, is that correct?
Well, before it was the Google Knowledge Graph project. So what happened was I realized it was going to be very important to have some computer representation of general knowledge for things like bus schedules and menus of restaurants or names of people, or there's zillions of entities, and if you know about the relationship between those entities, then that helps computers sort of navigate through questions about them. That's a very abstract idea, and I started a company called MetaWeb, which actually built this knowledge graph. And sure enough, people started using it. And we had no idea about how to monetize it. I'm not really a business person. I just knew people would need this. And so we started building it, and very quickly the search engines started using it. And eventually it became clear that this was a critical technology, and Google bought the company. And that became the seed for the Google Knowledge Graph. And they expanded it. Now it has hundreds of billions of entities and the relationships between them. And an awful lot of what you get from Google, for instance, if you draw a Google map, all the information, the traffic patterns, where the streets are, where the restaurant is that you're going to, all of that information is coming out of the knowledge graph. What the bus schedule is, and you name it. And in some sense, it's just a rendering of information it gets from that. Or when you do a search, certainly the information over the side, that comes from the knowledge graph. But a lot of the search results also come from the knowledge graph, that they may not actually have the words that you had in your search string. So when Google first came out, it had this sort of textual keyword search. But now Google also does this semantic search that's based on the knowledge graph. And it interleaves those results into your search results. But some of your most relevant results may not actually even have the words in it that you had, because they're semantically connected to it. So they've kind of integrated it into everything they do. Obviously, ad placement. They want to know semantically what's associated with what you're looking at, that kind of thing. And so now I don't know how many hundreds of billions of entities they know about, but it's at least that. Last I checked, it was many hundreds of billions.
Wow.
Maybe more than that now. And relationships. So it knows about you, it knows about the building that we're sitting in, it knows about this company, it probably knows about the architect that made it, it knows about the government jurisdictions that tax it, and the set of relationships is useful for an awful lot of things, obviously, ad placement. But in some sense, it was a failure, because what I really wanted to do was create this knowledge graph for the world, because I think the world could use it. So although that was a financial success that we sold it to Google, it was a failure to solve the goal, because now it's a proprietary asset of Google's rather than a resource for the world. And I do think the world could, it's a shame that every company kind of has to reinvent their own version of it. It's a big waste of human effort. And it also, advantages the big companies and that can afford to build that kind of knowledge graph. And really, I think it should be a public good. I also have understood how to do it better. And in thinking about it afterwards, one of the big problems with that knowledge graph was that it did not have a rich enough representation of the provenance of information. And I think that we're getting to a point where we have a kind of crisis in what do you actually believe. There's too much wrong information out there. The recent advances in AI have really supercharged the technology for generating plausible lies or plausible untruths that are out there. And so the problem of deciding what to believe is getting worse, and it will get much worse. And I think one of the few tools that I can imagine that would help everybody would be if you had a graph of all the public knowledge, but public assertions of knowledge, and the provenance of those assertions. Where did it come from? Who said it? What computer program? What's the chain? If a certain program deduced it from this database, what was the database? Which version of the program was used? what's the person that ran it, that asserted and believed it, and so on. And I think that you need that kind of information to decide what to believe, because one of the things about the knowledge graph is it doesn't necessarily say what's true, it just says what did people assert. And so it can have contradictory information in it. So it's good to recognize those contradictions, but if it has a rich representation of provenance, then it can also help you judge which to believe, what to believe. And you also need that because what to believe also depends on why you're using it. So if you ask, is Taiwan a province of China? Well, the answer to that sort of depends on what you're going to do with it. While you're asking, what are you going to do with the answer? If you're printing out a map to be sold in mainland China, you probably want to do something different than, if you have a different application and, you're trying to list all the countries to which you're allowed to export this or that to, you come up with a different answer. So it made me realize that truth is a pretty complicated thing. But a knowledge graph should capture that complexity rather than trying to simplify it.
It's the technology behind this has enabled greater access to knowledge and information. It's really lowered those barriers to accessing all of that. But I think you're absolutely right. With that comes a huge amount of responsibility as well. And I think in this day of, quite active disinformation or, inadvertent misinformation, we've all seen the snowball effects of those things, on society, on science, through politics. And so I'm quite excited to see where your next bit of tech goes and how it's going to contribute to combating that. But I'm going to take a little step back, first of all. We are in your lovely offices in Boston at Applied Inventions. And one thing that really strikes me walking around here is clearly how much fun you all have and how that maybe drives a lot of the work that you do as well. You've already said one of your criteria is anybody excited in doing this project that has crossed our path? This has gone way back in your career, hasn't it? Because you've had a real history of tinkering, of creating toys, robotics, and that led to a really interesting role you had at Disney Research. Can you tell us a little bit more about that?
So at Disney, the reason I went to Disney is when it was clear Thinking Machines wasn't going to work as a company. I decided to take a vacation from computers. I had young children, and all my life I had kind of wanted to be a Disney Imagineer since I had
Me too.
heard the term. I thought that's a cool thing. I want to do that. So I knew some people at Disney, and so they offered me the job of coming to Disney, and I was like, but there's not really any job there that is exactly right for me. And they said, okay, we'll make up a job. And I said, okay, well, I want to be Disney fellow, because that was sort of vague. And I said, but it doesn't really work if there aren't other Disney fellows. So I said, would you also offer the job to Marvin Minsky and Alan Kay? And, I want some other people along to be Disney fellows. So they did that. So they actually hired all of us. And I was the only one that went there full time. And I was also the vice president of head of Imagineering. And it was a third education for me. So my first education was MIT. My second one was Thinking Machines. My third one was Disney. And Disney it was all about a bunch of things that I really didn't ever think about much in my technical education, because it was all about how do you tell a story? How do you keep people interested? It was about art. It was about, so it was a completely new set of ideas that I got exposed to. And so I learned a tremendous amount for the first few years that I was there. Eventually, I decided, that was really good to learn, but I didn't want to spend my life in that because unlike science, which is very truth-oriented fundamentally, entertainment is almost the opposite. It's fantasy-oriented. And so the appearance is everything. This sort of superficial piece of it is. The story is everything. So eventually I decided I've learned a lot here, but and it was a lot of fun building theme parks and things like that. But eventually I decided, no, I really want to go back doing more what I was doing at thinking machines, which is solving these big, complex problems. But by then I'd been at Disney, and I realized even a company as big as Disney doesn't really have the ability to have an interdisciplinary team of scientists and engineers. It needs to focus on its business. And I realized every big company is kind of in that state. I mean, maybe a few. Google has Google X, but very few companies can afford something like that. And even, when they broke up the telephone companies, nobody could afford Bell Labs anymore. But there really wasn't a place for that kind of interdisciplinary work. So that was the gap that Applied Invention was meant to solve, is to have a place to go to where you can take a complex problem without knowing what disciplines you're going to use to solve it, or maybe use a lot of disciplines to solve it. And I had also learned at Disney the kind of studio system where you have a core. When Disney makes a movie, there's actually only a few Disney people involved in it. They hire the director, they hire the writer, and they're not hiring strangers. There's a network of people that they work with the same people over and over. So I thought that kind of studio model would be good for making a technology company. And so that's how we work. We actually it varies, but we have less than 100 people here usually. And then but we have thousands of people that we worked with over the years as a kind of network. So we're the kind of studio, and when we do a project, we may not have the right microwave expert, but we know the right microwave expert because we worked with them on a different project. And so we're able to pull together a team of our internal people who drive the project forward, and the people who have the more specialized expertise that we can bring in to solve a problem. So yeah, it sort of gets some things I learned from Disney, and some things I learned from thinking machines brought together. And it's also kind of by design constructed to be fun. I mean, the big attraction that people come here is the opportunity to work on these kinds of projects. And so the people who are here pretty much, we have kind of zero turnover. If you like being interdisciplinary and working on a bunch of projects, there's not a lot of places you can do that. And we're one of them.
You talk about very much how Applied Invention is doing the stretching that thinking machines was doing before on a range of different topics and different projects. So people will come and they have a problem to solve and they have no idea how to do it. You have also spoken about having an established network of people, but looking around your offices, I know your turnover may be low, but you have quite a diverse pool, and you're obviously working towards maintaining a real diversity of thought. Right. So how important is it that we do that, especially with the challenges that we're facing around AI and its potential impact on society?
Yeah, so we do maintain that diversity of people, but it's interesting. What happens when you do a project is a certain percentage of the people actually get so interested in the project that they sort of want to stick with the project. So normally what we do is we bring them to the point where version 1 of the product is actually, or the service or whatever it is actually out there in the market working, and then we step away from it. But by then, there's few people who've worked on it who are actually really interested in that project. And so enough of them, we just spin out a little company to work on that. So actually, the number of people in the company, as soon as it gets kind of above 100, we spin something out. Yeah. And so we sort of keep it down to that core of people who kind of want to do that series of projects. So it's sort of, the problem kind of solves itself, because it's useful that some people go with the project actually, because there's continuity like that. But it also lets us stay small. So pretty much whenever we get up to that level where you would have to have another layer of management, we solve that problem by spinning out part of the company in one way or another, and getting back to that sort of core interdisciplinary team.
That sounds smart. I like that a lot. I just find it really fascinating that the way that applied invention works, the way that thinking machines work, it's quite different to academia, because you are very, very sort of, you're translating that research into reality. You're creating actual solutions, which I don't think academia often has the opportunity to do.
Yeah, there's some things, the general mechanism by which ideas get translated from sort of the academic discoveries into something in the real world is small startups. But the truth of the matter is that that's a very inefficient way of doing things, because small startups mostly succeed or fail not on the idea, but like how good was the vice president of sales, or how good were they raising money, or stuff that really has nothing much to do with the quality of the idea. And so this is kind of an alternate way of getting an idea to make that transition from kind of the scientific discoveries that are necessary to enable it to the actual problem. But we always come at it from the problem rather than from the solution. And there's one problem that academia has is that, of course, when you do a PhD, which is the sort of basic tool of producing things in academia, it's just the way the professors do it is through their PhD students. Yeah. Then what you come out with that is a solution, not necessarily driven by a problem. It's driven by a possibility of getting your PhD. Yeah. And so it's a contribution, but it's not necessarily a solution. In fact, it's almost never a solution. And so it's much better to come back if you're driven by a problem and you're aware of all of these contributions that people are making and all these new possibilities that have been created by academia, then you can say, hey, this one plus some old stuff that we knew how to do before is actually a solution. So we get to do it by the problem pull method rather than the solution push method.
What do you think academia can learn from organizations like yours, like X, the interdisciplinary doers and translators of research? What would you love to see? And is there a two-way exchange of skills and information there that you think society would benefit from?
So when I was in academia, mostly as a student, a little bit as faculty, but my technique was always not to go to the subjects, but to go to the people, always remarkable people. And so one of the things, like my thesis committee was Marvin Minsky, Jerry Sussman, and Claude Shannon, the guy that invented the bit, basically. And, these were people that I went to just because they were amazing people, not because they had any idea in common or something like that. And so academia is a home for these amazing people, but it has a problem that if you want to be in academia, you can't really say, well, I want to be a generalist. You have to say, I'm the very best at something. Otherwise, you're not going to get hired in a department. So it forces people into to be very deep in a certain area so that you can, get a sufficiently small area so that you can be in the very top, top expert of that area. So academia by its nature sort of forces this fragmentation. And in some sense, you could, once you win a Nobel Prize or something like that, then you can do anything you want, but it's sort of, that's the free pass out of that. But it's not many people get that free pass from, out of the specialization. And so people are kind of forced into that. And so I think a lot of people who probably have naturally broader interests don't really get to play that out in academia. So I'm not sure how to fix that problem, but I think that's the weakness of academia. And in fact, it's funny. I probably talk to people in different departments at Caltech and Stanford and MIT more than they talk to each other.
Oh, wow, yeah.
Because I'm kind of outside of it and I'm kind of a customer for all kinds of ideas. Whereas, if you're, a geneticist, you probably talk mostly to geneticists, or astronomers, you probably talk mostly to astronomers.
There is a real problem, I think, with the siloed knowledge aspect of academia. And I do hope things like doctoral training colleges and things that have elements of people from different disciplines may start to overcome that within academia. But there is a long way to go, and maybe academic industry collaboration may be one way forward.
Yeah, certainly academia is aware of this problem and tries to do interdisciplinary projects sometimes, but ultimately the motivation, the career paths are such that that's not really a good career path for a young person. It's something you get to do once you've established your career. And by then, you're usually so specialized and so interested in it, it's very hard to talk to the people who are also specialized and deep in those other areas. So I'm not sure really how to fix that in academia. There's certainly room for more companies like mine. I mean, there's a lot more work for us to do than we can take on, but I don't think there are a lot. It's hard to find others because, again, the best way to make money is actually, again, to specialize, to make something to be your best at. And so companies also have this kind of pressure of carving out a niche for themselves where they can be a very strong competitor, and that forces them to be known, even if they have lots and lots of resources. So even if you're like a General Motors or something like that, you really can't afford to focus on much except cars. And even a very narrow definition of what cars are, you probably can't even really afford to, think about what would cars be if they were more electronic, and you need a startup like Tesla to come out and do something like that. So it's interesting that we have set up a world in which people are strongly encouraged to become specialists. And what that means, too, is everybody always assumes somebody else understands something, but actually there's a lot of stuff that nobody understands. And technology has gotten complicated enough that it's almost become like nature. That it used to be that nature was this sort of magic thing, and we could kind of try to cajole it into doing what we wanted and try to get insights, but fundamentally it was magic. Life was magic, and technology was things we could understand. We could build them. We could see how a machine worked. But I think we're entering an age when technology and nature are kind of becoming entangled. So we're starting to manipulate nature, sometimes on purpose, like through genetic manipulation, sometimes on accident, like changing your atmosphere. So nature is no longer something natural. It's a lot of stuff that is influenced by our intervention, our construction. And technology, because it's starting to get so complicated and people don't understand all of it, and it's beginning to use these techniques like neural networks or simulate evolution, or it's producing these incomprehensible things that nobody understands. And so it's becoming more like nature. So we're entering what I call the age of entanglement, where what's natural and what's technological, it's that dividing line is kind of disappearing. And it's all just sort of complicated. And so we're sort of finished with the sort of enlightenment idea that we would understand nature and get all the rules and push everything in the domain of understanding. Actually, kind of the opposite has happened. That we're now building things so complicated we don't understand them. It's a different relationship with the world.
Yeah. I'm a bit conscious of us stealing too much of your time, but I have two questions that I would love to ask you.
I'm sorry, say that again.
I've got two questions that I want to ask you. The first one is, we have talked about interdisciplinary research, but this goes beyond just research. We're 65 years beyond C.P. Snow's Two Cultures lecture of, science and the humanities and the arts going in opposing directions, and people having to choose tribes almost. But you have created something that gives you an opportunity to very much bring both of those things together in the Long Now Foundation. Can you tell us a little bit about what prompted you to set that up and what you're doing?
Well, so I guess, again, I was sort of lucky that I was working on things where we had the freedom to not only make them technologically beautiful, but make them physically beautiful. So I'm very proud that, for instance, the first computers that we built are now sitting in the Museum of Modern Art, right? Because when there's a sort of inner beauty to the architecture, but there is also sort of an outer beauty to the artifact too. So to me, that's all part of the satisfaction of making something. If you look at, and I think it probably always has been. I mean, if you visit the London Science Museum and look at the original things that were built by Faraday and Maxwell, they built, actually somebody was building, or Hooke, people were building beautiful instruments, and really much more beautiful than they had to be to serve the function that they did. At first, there were probably a lot of the ugly ones that didn't end up in the Science Museum, but I think always I've sort of cared about that aspect of things. And I think I learned a lot about that too in Disney, of realizing the importance of the story of something. So a lot of times something succeeds or fails because it has the right story behind it. So that's a piece of getting people to relate to it and connect to it and accept it, and so on. So, so that's always been important to me. And some things that's maybe the dominant thing. I mean, like one of my favorite projects is this 10,000-year clock that I'm working on. And I've been working on it for decades. And it really has no practical use, but it's really a story. And it's a story about how it's an acknowledgement of the human story, that we're part of something much bigger that goes back tens of thousands of years and will probably go forward tens of thousands of years. And so that's a piece of technology that is in some sense connected to that story, somehow tells that story or reminds people of that story. And that's kind of its sole purpose. So that's maybe the most extreme I've gone over onto the pure aesthetic side of it. But I think that's also partly why people like you working here, because I think we value making things that we care about. And so and what makes you care about something is more than just the problem it solves. It's sort of the aesthetics of how it solves the problem.
Wow. Okay, final question. Usually I ask people what the biggest challenge is that we're facing in society, but I'm going to turn it around a little bit for you, because you're such a practical doer and you work with amazing people and you find solutions to things. So what challenge are you most excited about solving in the next 5, 10, 20 years?
So if you look at what's made the most difference to the human condition, it's been that we've learned how to decide what to believe. That's what science is. Science was a new way of deciding what to believe. And that caused this explosion that we're in the middle of now. But recent technology has actually made that problem easier in certain ways, like search engines, but harder in other ways, like LLMs making stuff up that's plausibly true, but is just made up. And so I think that we need our infrastructure for deciding what to believe has gotten overwhelmed by the knowledge that's been produced and the misinformation, and it will be even worse by the misinformation that's getting produced. So I think that there's an opportunity to put in a better infrastructure for deciding what to believe. And I think that's the thing that will have the most impact on sort of the human condition. Because really, if you look at, what has humanity produced that's most valuable, it's actually our knowledge. That's what separates us from, people in prehistory, is knowledge. And I think that it's the biggest challenge, because I think it's being challenged in many ways, but I also think there's huge opportunities to use these same technologies that are sort of making the problem worse to make the problem better. And so I do think that we will we'll start using machines to represent all knowledge, the provenance of the knowledge, how to reason about that provenance and decide what to believe and change what to believe as new information comes along and so on. So I think that we'll have the ability to kind of supercharge the scientific process, but we're going to go through a phase of getting sort of bogged down in the muck before we, build the technology to rescue ourselves out of it. So we're at that exciting opportunity when the problem is just becoming apparent. And the solution, the pieces of the solution are there, but we haven't yet pulled it together. So I think that's going to be the great opportunity over the next few decades.
Well, I, for one, cannot wait to see how you tackle that and the impact that it has on society as well. Danny Hillis, thank you so much for joining us today. I really appreciate your time.
It's a real pleasure. Thank you.